Section 3.8 Liquefying gases using an isenthalpic expansion. Isenthalpic means the enthalpy is held constant. In this case, delta T over delta P is the so-called Joule-Thomson coefficient. Mu Jt. If mu Jt is positive, we can lower the pressure of the real gas to lower its temperature. If the temperature decrease is large enough, the gas can be liquefied. Experimentally, how do we liquefy a nitrogen gas at the room temperature? First, we need to compress this gas to a very high pressure, let's say several hundred atm. During the compression, the gas temperature increases. And then we can easily cool this high temperature gas down to the room temperature. This step actually takes energy away from this gas. And it's easy because we can just use room temperature liquid water to bring its temperature down. And now we need to cool the high pressure gas down to 50 K above its boiling point. So if the boiling point, let's say, is 80 K, we just bring the temperature of the gas down to 130 K. Okay? How do we do that? We'll talk about this later. And then we pass this high pressure gas at 130 K through a nozzle and allow this gas to expand suddenly to reach a final pressure of 1 atm. So the pressure of the gas drops from 300 atm to 1 atm. That's a huge pressure decrease. That will lead to the temperature decrease, hopefully as much as 50 K. And that will bring the gas temperature down to below its boiling point. All right? And during this process, the gas is liquefied, so you have liquid nitrogen, as long as the pressure decrease is significant enough. All right, once you have liquid nitrogen, it starts to evaporate, right? And the nitrogen gas from the evaporation of the liquid nitrogen has a very low temperature. And that low temperature nitrogen gas can be used to cool the high pressure gas down to maybe 130 K. All right? So that's 50 K above the boiling point of nitrogen. So this is the experimental description about liquefying a nitrogen gas at the room temperature. You need a really good compressor. So this compressor will convert this nitrogen at the room temperature in 1 bar condition to a very high pressure and very high temperature, so that you can use just room temperature liquid water to lower its temperature back to room temperature. This is to take away energy from the nitrogen gas. All right? And then over here in step D, this is to use the Joule-Thomson experiment, that principle, to lower the nitrogen temperature to below its boiling point. So over here, this is a diagram. You have nitrogen goes in, the compressor make it really hot, really high pressure. And over here, you can just use liquid water at the room temperature to bring the temperature down to maybe the room temperature, 290 K. And then over here, this 298 K nitrogen gas is cooled to maybe 130 K, 50 K above its boiling point. And over here, this is a nozzle. The high pressure nitrogen gas experiences sudden pressure drop from 300 atm to 1 atm. Over here, the temperature of the nitrogen drops further from 130 K to 80 K or even lower. It becomes a liquid. And this liquid, evaporates over here. This very cold nitrogen gas help to lower the temperature of nitrogen gas from the room temperature here, this is the room temperature here, to 50 K above the boiling point. And we need to be sure that the mu Jt is positive. For nitrogen, it's easier to find the region where the Joule-Thomson coefficient is positive. Very large region across a wide range of pressure and temperature. For hydrogen, it's a little bit more difficult, because remember, we actually need the attraction to be predominant to have a positive μJt. For nitrogen, it's easier. For hydrogen, it's more like an ideal gas. The attraction between hydrogen molecules is much smaller than attraction between nitrogen molecules. Okay, why is that? Again, when you have a nitrogen molecule, you have many valence electrons. They are farther away from the nucleus. It's easier to induce an instantaneous dipole in nitrogen than in hydrogen. So that's the reason.